Well, now we're going to go ahead and start on acceleration, and specifically acceleration in velocity versus time graphs and position versus time graphs. But we're also going to be talking about what is instantaneous velocity and also average velocity. And we kind of touched a little bit on average velocity a little bit, but we're going to get really heavily into it now. So if you haven't done the reading, please do so. Please read Coletta or OpenStax, or if you have the Survey or Nightbook, please do so, and please get started on your homeworks. All right, so let's talk about velocity versus time graphs. So let's take a look at this specific problem. You have a velocity versus time graph, and you have a velocity where it looks like it's got this low positive velocity right here. I'm going to go ahead and mark this up. Again, you hit the comments, then push that arrow back, and now you have these tools that you could use. You could change the color here, you could use the little pencil here. So over here, we have a velocity versus time graph, and it looks like here, and I'm going to break this up, this can be 0 seconds, 1 second, 2 seconds, and you've probably seen this in your lab book. 4 seconds. Okay. Well, and we'll call this 4, 3, 2, and then this will be 1. So this is 1 meter per second. This is positive 1 meter per second. Positive 1 meter per second right here. So it starts off with a positive 1 meter per second at time 0, and then it ends at positive 1 meter per second at time 2 seconds. And then something happens, and now it's traveling at positive 4 meters per second. Positive 4 meters per second, and positive 4 meters per second. Okay? Well, if an object starts at positive 1 meter per second, and then is ending up moving at positive 4 meters per second, typically, they don't do this jerky type of motion. Typically, they're gradually changing, and I'm talking about big objects like people and cars and planes and things like that, planes and boats. Typically, they don't instantaneously change, because here, this is really weird. At the 2 second mark, it's both got a velocity of positive 4 meters per second, but also positive 1 meter per second, which isn't possible for a big object. Particles could do this. Particles, atomic particles could do this, but not big objects like us. So typically, they start off at 0 seconds, and then they're going a little bit faster at 1 meter per second, and then at 2 meters per second, and they're gradually increasing their speed over time. Okay? And so this is what is called acceleration in a velocity versus time graph, right? And let's just make this easy. If this took 2 seconds to do this, it started out at 0 meters per second at 0 seconds, and then it's going 4 meters per second at 2 seconds, and it did that at a constant rate, you would have to say that this object's slope here is the acceleration vector, and that slope would be 2 meters per second squared, or it's this object's speed is increasing by 2 meters per second for every 1 second, right? From the 0 second to the 1st second, it was going at 0 meters per second, and now it's going 2 meters per second. So that added 2 meters per second to 0 meters per second. And then after the next second, you're going from 2 meters per second to 4 meters per second. So that is a constant slope. And the great thing about velocity versus time graphs is you could see not only the displacement, which we learned earlier, which is the area under the curve, right? So this area all the way to the 0 mark, okay, is the displacement, okay, but also you could since it's a linear equation, and we're going to only be dealing with linear equations as far as creating equations in college physics courses, we're going to be, it'll be really easy for us to recognize the acceleration component in there. So these two graphs are similar in that they're both increasing, they're both changing their speed, but this one is impossible for big objects. It really is. But this is actually more representative of how actual motion is. And we are going to be having changing velocity versus time graphs. There might be some curves, so just that we could illustrate some points, but they'll only be conceptual. Okay. So accelerated motion in a position versus time graph is a little bit different. But before we do that, let's talk about in acceleration versus for acceleration versus time graph, a positive slope. If you have a positive slope, that is a positive or rightward pointed acceleration vector. Okay, so this object, since its velocity vector, so it's all its data points are in the positive part of the graph. It starts out here at, like, let's just say positive 1 meters per second. Now it's going positive 3 meters per second. Then you could say that it's speeding up, right, in the positive direction. Well, if you notice the slope here is positive, well, that tells you that it's got a rightward pointed acceleration vector. So anytime your slope is positive in a velocity versus time graph, that is indicative of a positive acceleration or a rightward pointed acceleration. And in this case, this is speeding up in the positive direction. So that means you've got positive velocities, but a positive acceleration. Okay. The antithesis is this. You have a negative 3 meters per second, and then in the end, it's going negative 1 meter per second. Well, its velocities are all in the negative part of the graph. But if it starts out at negative 3 meters per second and then is going a negative 1 meter per second, doesn't that tell you that you had to add 2 to this to make it equal to negative 1? Well, this is telling you that this positive slope in this velocity versus time graph is the acceleration vector. Okay. And so even though it's traveling in the negative direction, all of its velocity vectors are negative, it has a positive slope, and that is slowing down. Okay. Over here, it starts off at positive 3 meters per second, and then it ends up going at a positive 1 meter per second. Well, if you start off at positive 3 meters per second, and then you're going at positive 1 meters per second, you had to subtract off a negative 2 meters per second from that, correct? Well, that tells you that means that slope is going to be negative 2 meters per second squared. And that means this acceleration is going to be negative. Okay. And so even though it's moving to the right, because all of its velocity vectors are positive, it's accelerating to the left, and that is called slowing down. Okay. Over here, you have a negative 1 meters per second, and it ends up going negative 3 meters per second. Well, all its velocity vectors are in the negative direction, and you're adding to that a negative 2 meters per second from the initial negative 1 meters per second, so it becomes negative 3 meters per second. Well, that is speeding up in the negative direction. Okay. So if you look at all these little data points right here, all these little data points, those are your instantaneous velocity vectors. Okay. And what that tells you is all of these little lines right here are showing a dot and a tangent to that line. In this case, it's just going to be along that line since it's a straight line. These are instantaneous acceleration vectors. Okay, so if you have a bunch of instantaneous acceleration vectors, okay, you could take and there is a straight line. Then in this case, the instantaneous acceleration vectors will be your average acceleration. Okay. So this is a cool way of actually seeing any changes in your acceleration as well. So if you start getting a curved line in a velocity versus time graph, then your velocity, or a change in your velocity versus time graph. So for example, your velocity versus time goes from pointing up and to the right and then down and to the right. Well, these are two different velocities. So now your instantaneous velocity vectors here are going to be different from the instantaneous velocity vectors here, and now your average velocity won't be equal to those. Okay? In a position versus time graph, we have a similar type of situation. Okay? So for example, this is 1 meter, it's 2 meters, 3 meters, 4 meters. Okay? And this is 0.25 seconds, 0.5 seconds, 0.75 seconds, and 1 second. So what it's kind of looking like is that this guy has a slope of positive 2 meters per second, and then all of a sudden that slope doubles to positive 4 meters per second. And that's what I'm kind of looking at. So this is going to be 5 meters minus 1 meter, 5 meters minus 1 meter, all over 1 second minus 0.5 seconds, so that'll be 0.5 seconds. So this is going to be 4 over 0.5, so that's actually going to be 8 meters per second. 4 times 2 meters per second. Wow. This guy was going from, this is going to be 1 second, 1 meter minus 0 meter, 0 meters over 0.5 seconds minus 0 seconds, which is going to be positive 2 meters per second. So this slope is slow and this slope is very fast. Well, again, you typically don't see motion like this. Typically, motion, if something is speeding up in the positive direction, takes on, in a position versus time graph, a more curve. So all these instantaneous velocity vectors will be gradually changing over time until they become this one. And this is positive 8 meters per second. And notice I try to make that slope the same as this slope. And this slope right here, I'm going to call positive 2 meters per second, and it goes along with this slope. So these are all the instantaneous velocity vectors, right? And the slope right here, if you look at it right here, this has an initial velocity, is the initial slope at time 0 of 0 meters per second. So in this case, when you're creating these curve fits, and put a dot, and let me erase that and do that again. In a position versus time graph, if I write the equation here, it's x final equals x initial plus vi. I should put vit plus 1/2 at squared. This is the initial position at time 0, and this is the slope at time 0. Okay, so its initial position is 0 at time 0, and it's got an initial slope of 0 at time 0. Okay, so this is a way to look at motion in a position versus time graph and create graphs from that. Now, again, what you're doing is you're seeing more of a gradual change over time, and that is, we are creating these initial so your initial your curve fits. So again, at this point in time, at time 0 seconds, this is your initial position at that point in time. And so your instantaneous velocity at that point in time is your initial velocity. So in order to get this component right here, you have to note the initial position, but also the initial slope at that 0 second mark. And that tells you both of these two components. And from there on out, the acceleration portion is just going to be changing your motion by this amount every second, right? So it looks like this acceleration is adding a velocity vector to it every point in time, and now your instantaneous slope, your instantaneous velocity is kind of curved up into the right, and it's getting a little bit more steeper over time. So if your slope is becoming more positive over time, so this is a positive velocity, this is 0, and then becomes a little bit more positive, and then becomes even a lot more positive. Well, now you could say this object is moving to the right because its velocity vector is positive the whole time, and it's becoming more steeper over time, so that means its acceleration is also to the right, and so that is speeding up. Okay? Well, here are all the different types of velocity vectors, position versus time graphs that we're going to be using for positive positions. Now, if you notice, again, you have your little slopes are increasing, and so this is that one case here where we're talking about where we have positive velocities and positive accelerations. So this is speeding up. Okay, here we have a negative velocity. So this is a negative velocity, and it ends up becoming it starts off with a very negative velocity and then a somewhat negative velocity. So these are going to be negative velocities that are decreasing over time, or are becoming more positive over time. So that means it has to be a positive acceleration vector, which goes along with this graph. And this is going to be now slowing down. I'll actually change this to, let me write the full-on speeding up in actual letters. Speeding up. Over here, you start with a positive, a very steep positive velocity vector, and it's becoming less steep over time, and it's only at just a little bit positive. So these are positive velocity vectors, but negative acceleration vectors. So this is also slowing down. And over here, you start off with it looks like a negative velocity vector, and it's becoming increasingly very negative. So that means these are negative velocity vectors, and it's becoming increasingly negative. That means that acceleration vector is continually subtracting from that and making it even more negative. So this is speeding up as well. And so these are how accelerations are affecting your position versus time graph, but also your velocity versus time graphs. Okay? So what's the difference between instantaneous acceleration and average acceleration? Okay? Well, here we have a velocity versus time graph. And if you'll notice, this is one of those situations which we don't come across often, but where your velocity is continually changing over time. So at this point, your instantaneous velocity is going to be pointed very steeply up and to the right. And then over here, if you look at it, right about here, your velocity is pretty much 0. So this is going to be a very, your acceleration is going to be 0. Should back that up a second. So at this point, if you'll notice in this velocity versus time graph, the slope, which is acceleration, is 0. But here, you have a very positive acceleration. And it starts to become smaller over time until you get to right here. And then right here, at this point, your instantaneous acceleration is negative, which over here looks like it's the same number but positive. Okay, so these two acceleration magnitudes would be the same, but they're different signs. One is going to be a positive acceleration vector, means an acceleration vector pointed to the right. This acceleration vector is going to be pointed to the left. and then that starts to change over time, okay, and become 0 again. Well, your average acceleration is going to be where your initial velocity vector was, and let's say over here, here's your final velocity at that point. Well, your average acceleration is just going to be your initial velocity minus your final velocity over, and let's say this occurs at t5, t4 is going to be right there, over your t5 minus t1. So this would be your average acceleration over that 5 second minus 1 second mark, okay? And in a way, that's kind of what we're doing to find your average acceleration, right? You take your initial velocity, you take your final velocity, and you basically are adding those together and then dividing them by the total time. Okay, well, you're subtracting those and dividing them by the total time. Essentially, your average acceleration is dv, is your delta v over delta t, your change in velocity over change in time. And it doesn't care about what happened in the middle. If you notice this changed all over this over here, but all we cared about is what happened at t1 and compared to what happened at t5. All right, and while your instantaneous velocities were changing at each one of those points, your overall average velocity just cared about what happened at the beginning to whatever happened at the end. Okay, and that's the difference between instantaneous velocity and average velocity. Well, let's go ahead and see if we could actually see what those are. So what we're going to do is we have a problem, and in this problem it says we're supposed to categorize these. This is going to be a y position versus t graph. So this is a position versus time graph, but in the y direction. And so we're supposed to try to answer these questions. At which label point, A, B, or C, does this, and it's an elevator, which means it's probably going up and down, has the lowest speed, which is the magnitude, not the velocity, but it's the magnitude of the velocity vector, so it's speed. At which point does the elevator have the highest speed? And then we're supposed to try to approximately sketch a velocity versus time graph for each one of these points. So I want you to evaluate the speeds at each one of these labeled points, A, B, and C. And actually, you could probably tell me which direction is it moving, up, down, or not moving at all. Okay, and I want you to then sketch a position versus time graph in the y, a velocity versus time graph for velocity in the y direction over time for each one of these points. So go ahead and try this out and see what you're doing. Okay, well, let's take a look at it. Here at A, if you look at the instantaneous velocity, and instantaneous means tangent, okay, that looks like it's pretty level. So in this slope, this velocity in the y direction at A looks like it's pretty much 0 meters per second. And C kind of looks like that too. Velocity is also 0 meters per second. This slope at B, even though it's at a position of 0 meters, as far as it looks like it's going to be on ground level, this is underground. So let's call this -1 meter, or -1 story. And this is above ground by 1 story. Anyways, this looks like at the velocity in the y direction for B, it looks like it's going to be very positive. It's a positive velocity, okay? So graphing this in a velocity versus time graph, velocity in the y direction, so this is going to be 0 meters per second. A is going to occur right here. So A, B, and C are almost times. It looks like it has no velocity at A. Actually, at the very initial time, it looks like it has a negative velocity. And then it has no velocity at A. And then it looks like it has a positive instantaneous velocity at B. and then no velocity at C. Okay, so I'm just looking at the slopes at these points. Slope here is negative, here's the slope is 0, this slope is positive, the slope here is negative, and that is going to be almost like little y-intercepts here. It's negative here to coincide with this, then it becomes 0, and then becomes positive, and then it becomes negative again. Okay? And so it looks like out of points A, B, and C, A and C, it's not going to be moving at all. So those are going to tie for the least speeds, and that B is going to be tying for the fastest speed. So those look great. And moving on to the next one, it looks like what we have is drawn correctly. So that's pretty cool. So you can see the utility of using position versus time graph and velocity versus time graphs, and also how to create curvilinear graphs in position versus time graphs, and then using that to draw your velocity versus time graphs. Well, let's try that again, but with a somewhat a more advanced problem. Okay, so here we have x positions, so this is going to be left-right motion versus time, and it looks like you're going to have to translate this. It's a car moving on a stretch of road. You're going to have to translate all of these points to this velocity versus time graph, which I've put right here for you. And so I'll mark this with A, B, C. I'll try to make it even. C, D, and then point E is really far out. Okay, and see if you could do that. And then here you're also try to say, where's your displacement going to be 0? So you're supposed to answer these questions. Where's your displacement 0, or where's your position going to be 0? It should be position is going to be 0. I'll change that for your document. Where's your speed 0? Where's your speed increasing? And this could be positive or negative, right? It just says your speed is increasing. Where's your speed decreasing? And this could be positive or negative. So try to evaluate which one of these conditions are happening. Okay? Pause the video now. Well, let's go ahead and let's try to graph this out first in a position versus time graph. So it looks like it starts off with a high positive slope. So it means it's going to have a high positive velocity initially. And then at A, that positive velocity is going to be a little bit lower. And then at B, it looks like it is 0. So it looks like the velocity is doing something like this. And then at C, it looks like it's now becoming, so I'm looking at the instantaneous velocities, and I'll use a different color to do that. So I'm looking at the instantaneous velocity, so that's a positive instantaneous velocity. The initial velocity is positive, but a little bit more. This is going to be 0. This is going to be negative, and this is going to be very negative at D, even though your position is 0. And then at D, it looks like you are not moving at E. It has a slope of 0. Okay. Well, I'm going to translate those to over here. So at C and then at D, it's becoming increasingly negative, right? So it's moving to the left. It's got a negative velocity, and this is a very negative velocity. This is a velocity of 0. This is a positive velocity, and this is a very positive velocity. And then over here, this is 0. So these are really negative, right? So this is a positive velocity. This is going to just be a positive velocity. Here's where your velocity is 0. C is a negative velocity, and D is a very steep negative velocity. And then something happens at E, or maybe even right before E. It then goes to 0. Okay. So your displacement, your position is 0 at the initial point, which is I, and I'll put that right here. I is right there. And then your position is 0 also at D. But your speed is 0 at B, and then at E. Where it looks like my speed is increasing is from B to D. And where my speed looks like it is decreasing is from A to B, right? Because it's becoming less slope. And here now it's becoming more steeper. And then from D to E, it looks like the speed is decreasing over time. So what I want you to do is go through these exercises and kind of, what you're really doing is practicing on what is instantaneous velocity and recognizing the slope from position versus time graph, and then translating that to a velocity versus time graph. And that gives you a sense of what these are happening. Here, it looks like you have a constant acceleration that is going to be a negative acceleration because that slope is negative. And then here, your acceleration is going to be positive. Okay. So it's really cool graphing this out. You could actually then create your equations from this. Well, now I want you to apply what you've learned. So I want you to merge everything that you've done together. So I want you to establish, here's your motion diagrams. I want you to match up these letters to these position versus time graphs, and then I want you to use that to create curve fits for your position versus time graphs and also velocity versus time graphs. And on the next slide, you're going to do the same thing, match up motion diagrams to these velocity versus time graphs, and then create equations for each one of those. So please go ahead and try that now, both of these two slides, this slide, and then we'll go back through it together. Okay? Okay, here we go. So here's what we've done. Let's go ahead and try to match up these motion diagrams to these position versus time graphs. And this would be horizontal position versus time because of the X. All right. Well, this first object, all these velocity vectors are going to be positive. So I'm going to put a positive velocity. And then they also seem to be speeding up, which means that they also have to be accelerating. Okay? So that means, let's take a look at it for a second. It starts off with a low initial velocity. So this right here is this instantaneous velocity at this point. So at time 0 to 0 to 1 seconds, this is the instantaneous velocity at that point. And then it's going to be a low, it'll be somewhat low, positive slope. And then it becomes very steep. In fact, it looks like it's going to be 5 times steeper, right? Because I think we talked about this is 0, this is 1, and this is 5 times the length. So this is positive 5 meters per second, and this is positive 1 meter per second. It did have a small slope in the beginning. So it looks like A is going to be matched up with number 1, which means it's got a positive velocity vector and a positive acceleration vector at each one of these. And these are the curve, this is the curve fit for this velocity versus time graph for number 1. All right. I'm going to erase those, and let's try graph B. Graph B starts off with a positive 5 meters per second, and it ends up at a positive 1 meter per second. So it starts off with a high positive slope, so it'll be a positive velocity, and ends up with a low positive slope. So this thing is slowing down. That means it has a negative acceleration. Well, something that has a high positive steep slope is going to look something like this, which looks a lot like this. So at time 0, something has to have a high positive slope. And then over time, that slope decreases almost to 0. This is positive 1 meter per second, and this is positive 5 meters per second. So this is going to be matched up with A. Looks like 5 is going to match up with B, and it's going to be a positive velocity, but negative acceleration, negative acceleration. Cool. Let's try C. C starts off with a negative 1 meter per second and ends up at a speed that is 5 times its original speed, but to the left. So that means we're going to be looking for an initial speed that is negative and level, which starts to look, so I'm going to look at the data points here, here, and here, as well as at this point. So I'm identifying all the initial dots, the initial y-intercept, and the slope at that y-intercept is what I'm looking for. So this one looks like it has a somewhat negative slope, and then it becomes very steep, negative 5 meters per second. So it looks like this is going to match up with C, because it looks like C starts off with a negative velocity, and it's speeding up, so that's going to have a negative acceleration. That means this is going to be negative, this is going to be negative, and everything's going to be negative. Your velocity components are going to be negative, and your acceleration components are going to be negative. All right. Let's try D. D starts off over here with a high negative slope, so it's going to be a very steep negative slope, and a somewhat level negative slope. So this starts off with a very steep negative slope and ends up with a somewhat level negative slope. So this looks like it matches up with D. Negative slope, but it looks like it's slowing down, so it has to have a positive acceleration. So that means the acceleration is adding to it and making it from negative 5 go to negative 1. So maybe over like a couple seconds, it gradually lowers its slope at each increment. Okay? And so that means your velocity is going to be negative and your accelerations are going to be positive. Cool. Let's try E. E has a positive 1 meter per second, and it looks like that size of that velocity vector isn't changing, so it's going to end up with a positive 1 meter per second. Well, I'm going to be looking for an instantaneous slope in the beginning and an instantaneous slope at the end, both the same as being positive. So this looks like it's going to be E, which means it's going to have a positive initial velocity, right? But it's got a constant velocity, so its acceleration is 0. So this component is 0 in both parts. It doesn't even have them. It's just this will be a linear, and this will be just positive initial velocity is a final velocity. All right. Well, F is the same. It starts off with a negative 1 meter per second, ends up with a negative 1 meter per second. So this is going to be just negative, and this is just going to be negative with no acceleration components. So that means its initial velocity is going to be up here of negative 1 meter per second, and its final velocity is going to be the same at negative 1 meter per second. So slope hasn't changed over time. So this will be F. And that's how you go through and recognize initial slopes at the y-intercept. And so this is a really good exercise to help you put together all of the skills that we've learned. Okay? Let's try it with the next one. I want you to do the same thing, but with a velocity versus time graph. And we've done components of this already, but I want you to do it formally now and put together all these together. Okay? So pause the video now and try this problem out. Okay, here we go. Again, you're going to have a positive 1 meter per second, ends up going at positive 5 meters per second, right? So this is going to be a positive velocity vector, positive acceleration vector, and that's going to be speeding up. B is going to be, so let's see which one is that. So this starts off at a positive 1 meters per second, ends up at a positive 5 meters per second. And so this has a positive acceleration, which probably goes with A, which looks like it's correct. So again, this is going to be a positive velocity vector, positive velocity vector, positive acceleration vector, positive acceleration vector. And this velocity versus time curve fit, linear fit, goes with these graphs. Okay? But if you have a positive velocity vector here, it has to be a positive velocity vector in the position versus time graph too. Okay? All right. Well, let's try this again for part B. Here we start off with a positive 5 meters per second, and it looks like it slows down to positive 1 meter per second. That tells me we have a positive velocity vectors but negative acceleration vectors, and that is slowing down. So I'm going to start off with a positive 5 meters per second here, and ends up being a positive 1 meter per second way over here. So that tells me that slope is negative, so that'll be a negative acceleration, which matches what I'm seeing. So these velocity vectors will be positives, and those acceleration vectors will be negatives. All right. Let's try it with another problem. Let's do C. This is going to be negative 1 meter per second in the beginning, traveling to the left, very short, and 5 times that size to the left. Okay, so it starts off at negative 1 meter per second, and it goes to negative 5 meters per second. And this would be a negative acceleration, so this looks like it's going to match up with C. I'm going to put a B here. It's matching up with B there. And so you start off with a negative initial velocity vectors and end up with, and so it becomes even more negative over time, so that means your acceleration must be negative. Okay? And so these are negative velocity, negative acceleration, and that is speeding up. Okay? All right. Let's try it with D. Okay, D starts off with negative 5 meters per second and ends up at negative 1 meter per second. So we're going to start off at a negative 5 meters per second, very negative, and end up at a negative 1 meter per second. Okay, so this slope is going to be positive, so that means we have a negative velocity vectors the entire time, but it's slowing down, which means the acceleration vector has to be positive. So this is going to be D. And these are negative velocity vectors and positive acceleration vectors. Okay? All right. Let's try E. We start off at a positive 1 meter per second. Those spaces seem the same over time. They're not varying. So that tells me that this is going to be a constant velocity. And those velocity vectors pointing to the right, that means the acceleration vector is 0, which means I have a positive 5, that positive 1, I don't know how much this is. Was that positive 3 the entire time? So this is positive, this is positive. These components are negative because our acceleration is negative. Okay? And F looks like, erase those. F looks like it starts off with a negative velocity vector and ends with a negative velocity vector. Oops, I forgot to mark this as E. This is E, and this is going to be F because it's our last one. These are negative velocities the entire time with no slope. So that tells me that the acceleration vectors are negative, and these are vectors are negative. So we have a negative velocity vector. Our acceleration vectors are 0, and this is a constant velocity. So I wanted you to try all of these and really practice putting together equations with motion diagrams, with curve fits, and a position versus time graph, but also velocity versus time graph. All right. In the next section, 1.2, we're going to work on accelerated motion, speeding up, slowing down, but also constant velocity in acceleration versus time graphs. And then we're going to start doing application problems, where now we're going to use all 4 equations of motion and apply to actual problems where we're actually going to be quantitatively solving. Okay? So hopefully you've enjoyed this, and so hopefully you've been able to have been given enough chances to put together really complicated information. Okay? See you next time.